Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much for the invitation. So it's about traffic flow, dynamical phenomena, and before I'm going to show you the outline of my talk, let me just tell you something about an experiment. So the experiment, you may have seen it probably. You go on a ring road, then you put cars on this ring road and you tell them to drive. And then after a while, t goes to infinity, what you see is a very special structure. So these cars drive with constant velocity and constant headway. The headway is the distance between the cars, okay? So now, if you increase the number of cars and tell them to drive, then if t goes to infinity, so it's not clear what happens, okay? And I show you a video on this. So this was done in Japan, and you may know this video. So what you see, the cars, they are driving, and we are in the, not in the first case, but in the second case, right? So what you see is some cars are braking stronger than they have to do, case A, case B, and it doesn't seem that we reach or approach a solution like in the first case, okay? So what you see is that there is kind of a density wave traveling backwards, okay? Which is well known in traffic flow. So density waves, they always travel backwards. They never go forwards. You are never overtaken by a density wave in traffic, okay? Okay, now my talk, the first part of my talk is about this. So this was published in New Journal of Physics. The experiment was done by Sugiyama and collaborators, and well, it was done already in the 90s and some more times in Germany, and the result was, I think, always the same. Now let me go back to my talk. So I will talk about a microscopic model. In the homogeneous case means the case without any disturbances like bottlenecks. So this is the case you saw in the video. Then the second part will be on the case where I introduce a bottleneck. Then I will talk about the macroscopic view. This is a special way to show microscopic results, and at the end I will talk about the future. And let me tell you that I'm not going to present you a new traffic model, and I'm not pretending that the model I'm going to use is the right one. I'm just using a very simple traffic model. So the aim here is different. What I would like to do is I would like to use a very simple traffic model and to explore the full dynamics of this model. And we know from traffic engineering that people often do the opposite. So they use more and more complicated models, but they don't really know in detail what the models can. So this is the other way around. So this is just playing like a mathematician, okay? Okay, this is the Bando model, proposed in '95 by Bando, and it's a microscopic model. You may know that in traffic flow many people use macroscopic models, so they use PDs. Some people use kinetic models, and here we use a microscopic model. So the xj is the position of the jth car, and the xj dot dot is the acceleration or the deceleration, is given by this term. So what the driver is doing, he's checking his headway. This is his headway, so the distance to the car in front. Then he knows about an optimal velocity function v. So and here the nonlinearity comes in. And according to this optimal velocity function, there is an optimal velocity for him. and then he compares it with his own velocity, and then he decides whether to brake or to accelerate. So it's a very simple idea, and well, you may say that probably we do not drive like this, but it's a model. To some extent,
Depends on where you are.
depends on where you are. Yeah, it's a model, and I will tell you about extensions of this model. So these are for sure very responsible drivers doing like that. Okay. Now, how do I close the ring? The ring road is here. So I have in the nth car. So the nth car is seeing another car in front of, which is the first car. So this is how to close these, to model this ring road, this experiment here. Okay, and this is a one example of an optimal velocity function. It's just a monotone increasing function reaching a maximum value V max. Now, this is something you know from undergraduate courses. So now we pass to other variables. We pass to the so-called headway variables, the yj, which are the differences between the xj plus 1 and xj. And we write it as a system of first order. And then we realize that there is a special solution. And there is another condition we have to satisfy, that the sum of all headways is the length of the circular road. And then there is a very simple solution saying that all cars have the same distance, L over n, which is a mean distance, a mean headway, and 0 relative velocity. And this is exactly the solution which is approached here. Okay? And well, now this is a question of stability of this solution. So now we talk about an autonomous ODE system, and we talk about stability of a fixed point. So that's why I said this is an undergraduate question. And this can be studied. Okay, if you study this, then you realize that you have to check the eigenvalues of the linearization. And if you do so, then you end up with a condition. And the condition is written down there. It's 1 over 1 plus cosine of 2 pi over n is something like v prime. V is the optimal velocity function of the mean headway. So if this condition is satisfied, then stability is lost. So it means that for low density, this special solution is stable, and that's why we see it. And for higher density, there is a critical value. This solution is not stable anymore, and we don't see it. Okay? Now, in reality, what people do is they increase the number of cars, taking the same circular road. Mathematicians, so what we do is we keep the same number of cars in order to have the same system, and we increase the number. So what you see here, only L over n is relevant. So we do it in that way. Okay? Now we would like to know a little bit more. So what happens at this point, at this critical value? And if you check the eigenvalues, what you realize is that, well, now you check the eigenvalues as functions of this special value v prime of L over n, which comes out to be a good parameter. And if you look at the eigenvalue curves, then you see that, for example, in this case for 5 cars, these curves, there is a pair of complex, a pair of 2 eigenvalues, complex conjugate pair, which is crossing the imaginary axis. So it means that I lose stability, and this is an indication that you have a Hopf bifurcation. Okay, and if you check the details of a Hopf bifurcation, then we realize that this is really a Hopf bifurcation. Hopf bifurcation tells you that in that parameter area you have periodic solutions. Okay, periodic solutions in what? In headway and relative velocity. Okay, now the question is, well, do I see these Hopf solutions here in this experiment? So then I have to check if these bifurcating periodic solutions are stable or not. Okay, and this is a little bit more tricky. So what one can do is one can study the so-called first Lyapunov coefficient, and if you calculate the first Lyapunov coefficient, then after a very long and tedious calculation, you end up with this very nice formula where you have the first, second, and third derivative of your optimal velocity function at that point, at that mean headway value. And if the sign, depending on the sign of these parameter, the bifurcating periodic solutions are stable or not. Okay, then you take the standard bundle function and you realize these periodic solutions are stable. Then you take another function which looks very similar and you realize they are not stable. So it seems to be, this is bad news, it seems to be very sensitive with respect to the choice of the optimal velocity function. But what we forgot is that the Hopf theorem is a very local theorem. Okay, this is just close around this very, in a very small neighborhood of these critical parameters. So if you want to know the full, so for the application you need to do the complete bifurcation diagram. Complete bifurcation diagram typically is done numerically, so at least I don't know about global bifurcation results in this case, so you do it numerically using special continuation methods, and if you do so then you get pictures like that, and what you see is, so this is just the left picture and then you blow it up and blow it up again. And what we studied right now was this point here. So here you have L, which is our bifurcation parameter, and you have some norm of the solution. So the line corresponds to the linear stability analysis, telling you that for big L, so low density, the special solution is stable, and for below the critical value you have an unstable special solution. So we call this solution quasi-stationary solution. Now at the Hopf point you have these Hopf periodic solutions which are bifurcating, but then if you do the global picture then you see that there is a turning point, and then you have unstable periodic solutions, and then you have again big oscillating stable periodic solutions. Okay, so this is an interesting picture, tells you that the critical value you obtained by a simple linear stability analysis is not the good value, because suppose you are here, then what you see is that your linear stability analysis tells you that you are still stable, but the global picture tells you that at this point you have coexisting solutions. So stable quasi-stationary solution, a stable periodic solution, and another unstable periodic solution. So in that case it depends on your initial data which kind of solution you are going to approach. It may happen that a small disturbance in the quasi-stationary area brings you to this big oscillating solution. So the traffic engineers, they always prefer the
just because I'm not quite sure what I'm seeing. All of the upper branch is stable essentially.
These only the dashed line is unstable. Yeah, the upper branch is stable. Yeah, stable periodic solutions.
It looks a little dashed at one point from my eyes.
So this part is unstable,
yeah,
and here it's stable. Okay? Okay, so seems that the nonlinear stability analysis gives you the right critical value, which should be here, somewhere here, and above that value you can be sure that you enter the quasi-stationary solution. Now these are some more pictures about the solutions, how they look like. Well, I can only show you a projection of the solution into the space of one car, for example. Then we have headway and velocity, and what you see is in this case you have this coexisting, or let's take this case, the stable quasi-stationary solution, the unstable periodic solution, and the stable periodic solution. But as I said, this is just a projection of the solution. Now if you remember this picture, then you know that, or then you may believe that there are other pairs of complex conjugate eigenvalues which are crossing the imaginary axis. Means that you have other Hopf bifurcations, and that's true, but then you bifurcate from unstable solutions and you get additional unstable periodic solutions. And this is from the theory, it's very clear But if you do numerics, it's very delicate because what you see is that if you have a big number of cars, then you may have many good eigenvalues in the sense that they have negative real part, and very few eigenvalues which have positive real part. And if you simulate, you may lie for very long time on an unstable periodic solution, but you don't realize it. And then after a while it changes, and at the end, if you simulate long enough, you always end up in this single periodic, stable periodic solution. And this was realized by people doing numerics on macroscopic models, and they realized in fact that they saw solutions, periodic-like solutions, and it changed after a while, and at the end they always got one single periodic solution, which is the stable one I've shown you before. The same can be done using microscopic models with delay, and there you have very similar results and similar bifurcation diagrams. Okay, now let me go to the second part. Let me introduce a bottleneck. A bottleneck at a certain position on the ring road. And so how do we introduce the bottleneck? We just reduce the maximum velocity around that point by some small value epsilon. Okay? And then we ask, so what is going to happen? So this solution will not exist anymore in general. It took us quite a while to understand what kind of solutions could be the generalization of the quasi-stationary solution in case of a bottleneck. And at a certain point then we realized that we have to look for very special solutions, so-called rotation solutions. A rotation solution is satisfying 1 here, means that there exists a time t such that for one turnaround, which is equal for every car at every time t. So this is called a rotation solution. Okay, and then in addition, now in this talk, I'm just talking about cars which all do the same, and if this is the case, so every car has the same optimal velocity function, and if this is the case, then we can look for solutions which satisfy also 2, means that every car behaves like the other one except a small time shift. But in general, this is not necessary to ask on a solution. The solution satisfying 1 and 2 is a very special solution. It's called pony on a merry-go-round solution. And this name comes from Aronson, Golubitsky, and Mallet-Paré, who used these kind of solutions in a completely different context in the 90s. Okay? And they called them ponies on a merry-go-round. Okay? Which is probably more appropriate here in a traffic context. Okay, so now looking for these solutions, the question is, well, first of all, how does such a, so ponies on a merry-go-round, we call them pumps. So pump solution, how does a pump solution look like? Now what you see here is x, and over x you see the velocity, and the red thing is the optimal velocity, the reduction of the optimal velocity around this point here. And then what you see is clearly that the velocity is going down, and then you re-accelerate. So this is a pump solution, okay? This is a pump solution. How can we find these solutions? Well, now you transform your continuous problem into a discrete problem. What you do is you fix a position x0, for example, and then whenever car 1 is passing that position, you take all the values of all the cars, means you take the velocity and the headway. And this is a discrete map. Every time car 1 passes position x equals 0, you take these values, you have a discrete map, and this is a Poincaré type map, okay? And a pump solution or a quasi-stationary solution is a fixed point of this discrete map, okay? So what we are doing here is we are looking for fixed points of this discrete map. Now, this picture should tell you, so in the case of no bottleneck, we had two types of solutions. So the quasi-stationary solution, which is this one, and the hot periodic solutions. Now, this is for epsilon equals 0, so no bottleneck. If you introduce a bottleneck, so the quasi-stationary solution becomes a pump, and the question is, what about the half periodic solution? And the answer is the half periodic solution becomes a so-called quasi-pump. Okay, and what is a quasi-pump? This is what I'm going to explain you in the next slides. So the pumps are perturbations of the quasi-stationary solutions, and the quasi-pumps are perturbations of the half periodic solutions. Okay, so how can we realize if we have a pump or a quasi-pump? Now let me show you some pictures. Well, maybe I told you that the pump is a fixed point of this special Poincaré time bed. A quasi-pump corresponds to an invariant curve in that picture. Okay, so in this picture, a pump would be a single point, and a quasi-pump corresponds to these closed invariant curves. Now let me show you again pictures. The same thing. Above on the left we have the quasi-stationary solution, so velocity is constant. This is the half periodic solution. Now here you have the pump, and the quasi-pump is something like that. So what you see is kind of a mixture between a pump and a periodic solution. But there is no special structure in this picture, okay? And that's why we try to find another way to represent these kind of solutions, because at this point it's not clear if you have a quasi-pump or not in front of you. And in order to solve this problem, we switch to another kind of representing solutions. This is basically the same solution, just another way of presentation. So what you see here is x, and you see t, and here there should be just one single color. What we do is we take the trajectories of the cars and we color the trajectories with the headway. Okay? And then we make very thick lines. Then it seems to be a macroscopic picture, but this is not a macroscopic picture. It's just a picture. It's maybe a little bit misleading. So it's a picture consisting only of microscopic data. Okay? And if you do so, this picture should be just one color. So this is a constant solution, the quasi-stationary solution. The half periodic solution, they come out to be traveling waves. And the pumps, they come out to be standing waves. So you have a standing wave around the bottleneck. And the quasi-pumps, now you get an idea what it is. So it's kind of a traveling wave which is deviated around the bottleneck. Okay? So in this picture it's very easy to realize a quasi-pump. Now let me go here. So right now the bottleneck was not very strong. So in fact I called it epsilon. No, but now you can introduce strong bottlenecks. So this is the bifurcation diagram. This is done numerically. So epsilon equals 0. So this is where we had no bottleneck. So we had the quasi-stationary solution and the half periodic solution. Now if you introduce the bottleneck, you get this bifurcation diagram. So the red curve is the corresponding bifurcation, so the bifurcation in the discrete problem corresponding to the half bifurcation. And this is a so-called Naimark-Zucker bifurcation in the discrete problem. So here we have quasi-pumps, and here we have pumps. And this black, or this dashed area, means that there we have additional phenomena. There are folds. I will tell you, I will show you now two special lengths. One is 18, which is here. So what we do is we go up here, and one is 13. We go up here, okay? And we see what happens. So now if, first we start with 18, okay? To check the page. So this is 18, and what you see is Vm is a mean velocity over epsilon. So it's clear that the mean velocity, if you increase the bottleneck, is going down. Okay, but what you see is that it's decreasing, and then you have two folds, and then it is decreasing again. So in that area, so we expect pumps, but for example here around point 3, we have two coexisting stable pumps and one unstable pump. Now let me show you the corresponding pictures. So this is now the pump for epsilon 0.2, okay? And in this picture you see, first time you see the trajectory, so these white lines are the trajectories of one single car, okay? So the car is, so this is X, this is T, it's going here, it's coming back here because the road is closed, okay? And here he's braking a little bit more, so the trajectory is not a line, okay? And this is the picture of the solution over X. Okay, now I increase epsilon, and if I increase epsilon, so the pump becomes stronger. This is epsilon 0.3, okay? The velocity is reduced more when passing the bottleneck, and here this is the same value of epsilon. So now we are in this region where we have coexisting pumps, okay? So this is one pump for the same value of epsilon, and this is another one. They are both stable. I don't show you the unstable, which is in between. So, and you see they have a different value of Vm, so of the mean velocity. One is 0.91 and the other one is 0.78. Means that depending on your initial data, you can enter one or the other pump, okay? So the second one is for sure the worst, the first one is the better one because you have a higher mean velocity, okay? Now we increase epsilon again, 0.4, then this bottleneck is very strong. You see it in the reduction of the speed, yeah? A strong reduction of the speed. Okay, now let me go back to L equal 13. So now we go in the area where we have the quasi-pumps, and then if we go up here at a certain point, at 0.35 we cross this Nymark-Zucker curve and we come back to the pump area, okay? So I go and show you the picture of L equal 13. So the red dashed line corresponds, so again the mean velocity is decreasing when increasing the bottleneck. So the red dashed line corresponds to the quasi-pumps, and then at 35 we re-enter the area of pumps and we have again two folds, and what I'm showing you now is just by increasing the value of epsilon how the solutions look like, and I'm only showing you these So this is for epsilon equals 0. This is the Hopf periodic solution. It's just a traveling wave, okay? Now, and you see the periodic structure here in the velocity, okay? Now we increase epsilon, 0.2. What you see is that, as I told you before, the bottleneck basically deforms a little bit this traveling wave, and in the velocity over length picture you cannot see any clear structure, okay? maybe, if you look at the white lines in the right picture, then you see that the white line is the trajectory of the car. Whenever you come back, you cross the bottleneck or this special wave at a different point. So every time you come back, it's different, and that's why you have this very special unregular structure in the solution, right? And now we increase epsilon, okay? And after a while, we have to pass to the bomb area. What you see is that the bottleneck is becoming stronger and stronger, and at a certain point, this distorted wave is going to be destroyed, and more complex structures are coming up. Okay, this is something which you may live in real life. So you have a bottleneck, and you have dense traffic before the bottleneck with a special structure, which you usually as a driver you don't see this structure. When you enter as a driver, you go along this white line, and every driver lives a slightly different story. Okay, if you go here, you brake once, and then, well, basically once. If you pass here, then you brake twice, and there may be positions where you have to brake 3 times. So this is a very complex structure. You only realize from the macroscopic point of view, but you don't see it as a driver. Okay, and now we go on. We increase epsilon, the bottleneck, and the structure becomes more and more clear. And I told you at epsilon 0.35, we go back to the POM area. And now we are again back at the regular POM solution. And you see the POM solution here with the regular structure. Okay? One more comment. If you look at these pictures here, there is a very interesting thing which we try to prove at the moment. Fix the position X in these special structures, and then we believe that you have some kind of periodicity in time. Okay, so just fix a position X, then you go up there, then you have some kind of periodic picture. For every X it's different, but you have some kind of periodicity. Okay, and again, so the picture is made simply by microscopic data. So it would be very nice to have an underlying PDE giving you that picture in order to check the periodicity, but this is not what we have. We have microscopic data, microscopic solutions, and we have to, at least in the first step, we have to define what we mean by periodicity, okay, in this sense, because you have only values, some values at a fixed X, okay? So this is still a very interesting question. We have some ideas of the proof, but it's not yet done. Okay, so let me go back to the to another story. 5 more minutes maybe. Then what about fundamental diagrams? So you know, or if you are familiar with traffic flow modeling, then you know that the fundamental diagrams are very important things. So you have flow over density. So this is a fundamental diagram, okay? And it seems to be strange to talk about fundamental diagrams in a microscopic model, because I put in an optimal velocity function, which is a very special fundamental diagram. But what I know now is that the solutions corresponding to that fundamental diagram, which give me back the function I put in, these are only the special solutions, and I know that these special solutions, they are not stable in general. So what I have to check is now I'm trying to use my model to mimic a measurement. Okay? To mimic a measurement means I go on a certain position x equals 0, and whenever a car passes, I take velocity and headway. Okay? And then I get a lot of measure points. And if I do so, I get these pictures here. Well, clearly I have to produce different densities. How can I produce different densities? I change the length of the circular road, obviously, so to have a row axis, okay? And then I draw this measured data, this simulated data in this picture. So flux over density. And what I see is, or what I should see, it's maybe not so easy to see. There is for small density and for big density, there is a remainder of the optimal velocity curve, okay, which was my input in the model at the beginning. And the rest comes from this area where I had the Hopf periodic solutions, and there I have a lot of data, okay, which have these, produce this cycle-like structure, okay. Now, if you look at this data, what you see is, maybe the second picture is the best one. If you look at this picture, then you see something which in the traffic community is called an inverted Greek lambda, okay? There is some lambda here, or, well, there may be some lambda there, okay? So, means that in this very simple bundle model, you already have this lambda structure, okay? At least a very rough version of the inverted Greek lambda. But it isn't there, okay? And it depends, and it strongly depends on the fact that you realize which solutions are stable and which solutions are unstable. Okay? Now, so when talking about measurements, you have to be careful. So what I told you is whenever a car passes the position x equals 0, for example, then I take the values. So a measurement device could also work differently, making a time average. And if I do a time average over 1 minute or 10 minutes, then my measured curves, they look differently. Then clearly I get still a fundamental diagram which is slightly different, okay? In that case I kind of average over the periodic solutions, okay? And again, what you still see is these, so this is a blow up of this picture in that area. What you see is the coexisting Hopf periodic solutions and the quasi-stationary solutions. And what you see here is that for a traffic engineer, it's important to drive you into the homogeneous traffic, into the quasi-stationary solutions, because there you have a higher flow, okay? In the case of the Hopf periodic solution, the flow is lower, okay? It's an important point to mention. Okay, now you can do the same game, putting on the bottleneck, and what you see is that these inverted Greek lambda structure is quite robust versus bottlenecks, and probably that's the reason why you can find it so often in the traffic literature. Okay, at the end, let me just put the same question as I already did. So what we would like to know is that these macroscopic pictures, we would prefer to have them as solutions of some PDE model, clearly, but it's not clear, or at least I don't know of any PDE model having such kind of solutions at the moment. The question would be to have a PDE model which is not too complex in order to be able to study such kind of questions, okay? And the last question I already explained, so what about this time periodicity for fixed x in the pictures? And at the end, let me just show you a few literature, and thank you for your attention. Thank you.
Okay, we have a lot of time, so are there any questions?
I was wondering, like, you had the situation where you had two pumps essentially, and there was an unstable one in between. How does it look like if you start, let's say, close to the unstable one numerically? Which one of the two pumps do you go to? Is the simple picture, a complicated picture?
Oh, it's not clear. So we don't know about the area of attraction of these two pumps.
But somehow this is sort of the essential engineering thing you want to have, right? You want
Yeah,
to
but
have the upper one, the most
Yeah, but you have to, so in the phase space, so this is a very big space. If you had 100 cars, you have a 200-dimensional space where you have to check the area of attraction. So this is what we didn't, we never checked, because the simplest, the lowest number we use are 5, so it's a 10-dimensional space already.
But I mean, all this calls for homogenization, doesn't it? Or a thermodynamic limit or something like that. I mean, you said PD, I mean, that eventually you want to get a PDE model. Now you have 1,000
Or even a kinetic model. Even a kinetic model.
Yeah, I mean something. But I mean, you have 1,000 cars and you basically write ODEs.
Yeah.
So I mean, that calls for
Sure.
thermodynamics, sort of, right? Thermodynamic limits.
That's true, yeah. So there are some formal passages to macroscopic models. And then you get some PDEs. But to my knowledge, it's not clear at all if those PDEs have this kind of solution structure. So at least people who are doing that, they couldn't tell me.
Small second question. Is something known about solutions which are not POM, or like you were saying essentially for POM or POM-like solutions?
Yeah.
I mean, maybe I understood it wrong, but it seems like this was sort of a premise. Now we look for these sort of solutions.
Yeah, and then the quasi-POMs, which is a much larger class of solutions.
But is there even is there something known that this should exhaust essentially all the dynamics? This sort of class?
Well, so the only way to find all the solutions, at least for me, is going via bifurcation. So whenever something bifurcates, then I can find other solution structure. So you can have period doubling and phenomena like that, but those solutions, they look similar to POMs or quasi-POMs.
If you want to get a global picture where you know some sort of...
So this is quite global, the picture. So what we don't know, if you have other kinds of solutions which are not attached to the bifurcating structures we have. So if something like that exists, we don't know.
There's no sort of experimental numerical indication that something exists?
Well, all the experiments we did, we always end up in one of those classes. So we have
So this is really
one of those 4
I
classes.
believe is the good things.
Yeah. But as I said, I mean, the space is very big, so there may be... So maybe I should say the advantage of this approach is that you can find these solutions. So if you don't have knowledge about the bifurcations, you never find these kind of solutions. It's impossible to get a half-periodic solution or a POM solution or a quasi-POM. It's impossible.
Any other questions? If not, we will have a break of 3 minutes. We start again at 3 and we then leave again.